As of April 1968, the various components of the J-2 engine system had been subjected to thousands of individual tests. More than 4,000 tests had been made of the complete engine system at ground level, under simulated vacuum conditions, in clusters, and at test sites other than Rocketdyne's Santa Susana Field Laboratory. More than 3,800 seconds of flight time had been accumulated on 10 J-2 engine systems, with all in-flight operations notably successful. Yet on the Apollo 6 mission, one of the 5 S-2 stage engines shut down prematurely, and the single engine in the S-4B stage did not reignite after successful first burn and orbital coast. The cluster of 5 J-2 engine systems in the S-2, the second stage, fired on schedule, and measurements indicated proper ignition and operation. Engine compartment temperatures were normal for the first 72 seconds of operation, at which time the temperature in the upper region of one engine registered a gradual drop. This was accompanied by a slight decay in engine performance. Approximately 3 minutes later, the temperature climbed sharply, engine pressure dropped, and the engine shut down. On the S-4B, the third stage of the vehicle, the single J-2 engine system experienced an almost identical sequence of events. Ignition and operation were normal. At 68 seconds, temperatures in the upper region of the engine decreased to a level similar to that experienced earlier. It was noted that isolated readings were as low as minus 400 degrees. The engine continued to operate to the planned shutdown at 170 seconds. After 3½ hours of orbital coast, it did not reignite on command. Highly skilled research personnel were drawn from all Rocketdyne resources to analyze and resolve the flight failure. A detailed review of flight data affirmed the proper operation of all major engine components: turbopumps, gas generator, thrust chamber, leaving the ignition system with its oxidizer and fuel feed lines as the possible source of the problem. The J-2 engine ignition system, generally referred to as the Augmented Spark Igniter, or ASI, consists of an igniter body and chamber assembly, 2 spark plugs, an oxidizer and fuel feed lines. The ASI is positioned at the center of the injector and ignites the main propellants in the thrust chamber. Data from the flight tended to focus attention on the fuel line bellows of the assembly. Isolated temperatures near this area were recorded at minus 400 degrees. The fuel line bellows consisted of a convoluted section supported by an outer braid. This construction allowed flexibility for installation and afforded the necessary strength for high rates of flow and pressure. With all data pointing toward a fuel bellows failure, an intensive program to isolate the cause was initiated. The immediate goal was to duplicate exactly, in ground test, failure data as recorded in flight. Following a series of calibration tests, a bellows failure was programmed into a J-2 engine system. Data from this test was compared with flight data, and temperatures, pressures, and performance shift were found to correlate very closely. As it did in flight, the engine continued to run for more than 100 seconds before shutdown. Supporting data was obtained through ASI assembly testing under a variety of ground-level conditions, with failures programmed into the runs. Information gained in these and in the engine tests continued to define a bellows failure as the source of the flight problem. At the same time, more than 300 component tests were made under similar conditions, but with failures not induced. They were conducted through the entire range, to extreme limits of flow rates and mixture ratios. They were made both with and without propellant flow, in a variety of environmental conditions, and at severe vibration frequencies. Individual components and an entire J-2 engine system were subjected to this type of testing. In this series, no failures occurred. This served also to substantiate the findings of Rocketdyne review boards that quality of materials, fabrication techniques, welding, and workmanship were in accordance with stringent Rocketdyne and NASA specifications. It was clear that bellows failure was not caused by normal engine operation, material quality, or manufacturing processes. As these conclusions were being reached, parallel investigations were being made into a number of other areas, including bellows vibration as a result of fluid flow. Previous testing had indicated the existence of vibration resonances, that is, sudden amplification of stresses in the bellows as the rate of fuel flow varied. In terms of the bellows testing, the metal vibrated uniformly except at those times when its vibration frequency was in phase with that of the liquid hydrogen. At these points, vibration of the metal was amplified. Thus, at engine start with low flow rate, vibration of the bellows was uniform. As the flow increased, vibration was amplified at 1.1 pounds per second flow. Vibration dropped to the uniform level as flow continued to increase, then peaked again at 1.5 pounds per second, and again at 1.8 pounds per second. At twice the normal operating flow, the bellows failed. Significant, however, was the vibration peak at 1.1 pounds per second. This was within the engine operating flow range. With these vibration peaks plotted, and with ground tests showing conclusively that the bellows would not fail except under the most severe flow rates, tests were conducted in a vacuum to simulate the conditions of outer space. In 8 successive tests in this vacuum environment, the bellows failed within 100 seconds. In each case, failure occurred at the 1.1 pounds per second flow rate. From these studies, 2 conclusions were warranted. The resonant vibration peak was a critical factor, and testing at a ground-level environment was affording some type of protection to the bellows to keep it from failing. Protection that is not present in outer space. 2 factors are present in ground testing that are not present in the vacuum of outer space. One is moisture in the air. The other is air itself. Studies were focused on the effects these 2 factors might have on bellows operation. It was postulated that the extreme cold, minus 400 degrees, of the flowing hydrogen fuel was solidifying the moisture in the air, causing ice to form around the bellows during ground testing. This ice might then affect the bellows in some manner that would prevent a failure. Tests were made with a moisture-saturated, airless environment around the bellows. It was seen that this moisture did solidify into ice around the bellows, but the bellows continued to fail at the 1.1 pounds per second flow rate. It was concluded, therefore, that moisture alone had little or no effect on bellows failure. At the same time, tests were being conducted in dry, moistureless air. It was known that air turns into a liquid when it is cooled to minus 325 degrees. With liquid hydrogen at minus 400 degrees flowing inside the bellows, it was observed that on contact with the outer surface of the bellows, the dry air did turn into a liquid state. Increasing flow rates of the liquid hydrogen with attendant increasing vibrations were then induced, but there was no bellows failure. It was apparent then that liquid being condensed on the bellows was affording some form of protection to the bellows during ground tests, and it followed that the absence of air in the vacuum of outer space resulted in loss of this protection, causing the bellows to fail. 2 measures of protection were given by the liquefying air, and one can be identified through this cross-section of the bellows. During ground operation, air entered through the braid, and upon contact with the bellows surface, liquefied. The liquid accumulated inside the pockets and was trapped by the braid. This served to partially dampen the vibration at ground level. The second mode of protection was hypothesized through a mathematical formula. It was determined that heat, escaping from the cooling air, was being absorbed through the metal by the liquid hydrogen in the convolutions. This caused a lowering in the density of the fuel. It was determined further that this lower hydrogen density within the convolutions, as well as the liquid air on the outside of the convolutions, would restrict bellows vibration. An analytical model was formulated and was mechanized for solution on an analog computer. It was then shown that without heat, the situation in outer space, the bellows vibrated freely and would fail. Conversely, the application of heat into the convolutions gave a damping effect. To verify conclusively that this application of heat would protect the bellows, a series of tests was performed in an environment of heated helium. This approximated the heat transfer characteristics of air, but without the air itself to liquefy. In repeated tests, at varied flow rates of liquid hydrogen, the bellows did not fail. It was thus shown that heat, as well as liquid air, did protect the bellows by damping the vibration. The igniter assembly has been redesigned to eliminate this mode of failure. The new design incorporates a tube assembly without bellows, and these new assemblies are in place on all J-2 engine systems. These studies into the phenomena of cryogenic temperatures, the vacuum of outer space, heat transfer, and their effects on fluids, metals, and metal structures have included pure research. The information gained and data from studies that continue are being furnished to the National Aeronautics and Space Administration and to industry.